It's okay.
So lab 1, okay, so basically you need to know this unit. I'm sure you know this very well. It's 1 liter is 10 to the 6 microliter, and 1 liter is 10 to the 3 milliliter. And then the mole, all right, the molar mass, that's the mass in gram of 1 mole of that substance. And the molar mass calculates summing the atomic masses of all the atoms appear in the chemical formula, all right? And so, for example, if you have the sodium chloride, so where's the sodium? 23, all right? Chloride 35, so the molar mass is 23 plus 35, so it's 58, all right? So the molar mass is 58, right? 58. So that means the the number of mole N of a species X or molar mass MS is given by the N equal to the mass over the MS. So let's say the sodium chloride, if you have something 29 grams, so that'll be how many mole? Since we know the molar mass is 58, then the mole will be 29 or divided by 58. So that's 0.5 mole, all right? That's how you get the mole. The reason I teach you more is because the next concept is the molarity. For the molarity, you need to know the mole first, all right? And then you need to know the volume. So the molar concentration of solution of chemical species X is the number of the mole of that species that is contained in 1 liter of solution. So they say if you want to calculate the molar concentration of the ethanol that contain 2.3 grams of C2H5OH in 3.5 liter solution. So the molar mass is 46 and 2.3 grams. So you would do 2.3 divided by 46, right? So that'll be 0.05, 0.05, and then over 3.5. That would be the molarity. Okay, so that's how you determine the molar concentration. And then another two concepts that will be weight over volume percent. Okay, weight over volume percent. So that weight 100 grams of a solute per 100 milliliter. So that means if you want to prepare 1% of 50 milliliter agarose, so that means 1 gram per 100 milliliter. Then if it's a 50 milliliter, then it's a 0.5 gram. Okay. All right.
Are these the type of calculation questions we're going to get on next week's quiz?
Correct.
Okay.
And then another concept, the pH, acid, and base. All right. The pH, basically pH. Okay, pH. So remember, pH is negative log of the hydrogen concentration. So let's say the hydrochloride concentration is 0.1 m, right? The mole, right? Molar concentration is 0.1. Therefore, pH will be negative log, all right? Negative log of 10 to the minus 1, all right? And then minus 1, and because log of 10 is 10, so that'll be plus 1, all right? So that's how you get plus 1. And then the Henderson-Hasselbalch equation, all right? So that'll be pH equal to pK plus log the conjugate acid and acid, right? Let me see if we have that here. So remember acid in the solution, they dissociate. You have the hydrogen ion and the conjugate base. And then the Ka, the constant, reaction constant, will be H, the concentration hydrogen multiplied concentration of the conjugate base divided by the weak acid. All right, so this is the formula here, and then we bring it to here, right? This one, okay, the constant, reaction constant, hydrogen, conjugate base, weak acid, and then you take log on both sides. So that'll be log Ka equal to log H here plus log this conjugate base over the acid. All right, so that's how they derive this equation. And then you put negative on both sides. So you put negative, so negative log H. Actually, you remove this log H to this side and log K to this side. Therefore, it will be negative log H equal negative log Ka plus this same item here. And negative log K log H, that'll be pH, all right? pH, negative log H here. That's pH, all right? So that's give you the pH. And then this would be pKa plus the log of the conjugate base over the acid. All right, that's called Henderson-Hasselbalch equation, very important. And now let's go to this pH equal to pK plus log conjugate base weak acid. All right, and now we come to this question. So for example, if you have 1 mole of acetic acid, you titrate with the 0.1 molar of the sodium hydroxide, and then what would be the pH? All right, so the pH, okay, remember the equation will be acetic acid on the left side, and then on the right side you have acetate plus hydrogen. All right, and then the pH equal to pKa. Since you have 0.1 molar sodium hydroxide, therefore 0.1 of the acetic acid will go to this direction here. So you can think this way. So this is acetic acid, all right, and then hydrogen ion, acetate. So you have 1 molar here, but you add the 0.1 molar of sodium hydroxide. So that means you need to have 0.1 molar of the hydrogen ion. If you need this 0.1, then this 1 molar has to go this direction to give 0.1. So 1 minus 0.1, here's 0.9, all right? And then 0.1, 0.1, and here is 0.9. Therefore, the pH here for this one, pH equal to pKa plus log 0.1 over 0.9. All right? Did you all follow me?
Professor, do you have an option to have a pen and draw what you're writing? It's hard to just visualize the math on the screen.
That's a great question.
There's an option. I don't know how to do it, but I know it's there because our older professors used to do it.
Normally, if I do this at home, I have a whiteboard, but now I'm in my office. Let me see if I have whiteboard. I don't have whiteboard. You know what? I will write on the paper and then I'll show it to you. Okay?
Okay.
Just give me a minute. So I'm going to write it. This is very challenging. So next
Is there a pen option on top of the screen, on top of the whiteboard? There should be a pen option for you that you can do it.
No, before I learn it, I think I can just write it quicker.
Okay.
Probably take 1 hour to learn it. Okay. Okay, remember here is a log, okay, conjugate base, right, over weak acid. Okay, I'm going to turn on my video, okay, so you can look. And remember here, all right, 0.1 molar, okay, I only show you the 0.1 molar, right? And then, of course, you can do it the same for the 0.3, 0.5, 0.7. Can you read these? So from here, acetic acid, so dissociate hydrogen ion as acetate, right? And then you have 1 mole here. And now you add the 0.1 mole of the sodium hydroxide, 0.1. So 0.1 sodium hydroxide, that means you need the 0.1 of hydrogen ion. If you need 0.1 hydrogen ion, so that means you need to dissociate 1, all right? 1 has to come here. So 1 minus 0.1, so you have 0.9, and then 0.1 here and 0.1 here. And so that the pH now equal to pK plus log 0.1 over 0.9. Did you all follow it?
Yes, I'm following that
Good.
now.
Good. Very
So we're
good.
calculating the equilibrium constant here.
Yes.
Okay.
Okay. Good. So this is what you need to do. And then let me go back here. Let me see. Yeah. And then pH, of course, pH is negative log of the hydrogen ion activity. So pH is negative log H here, right? POH, that'll be least. And so the best, the reason we learn the pKa, pH, because in the molecular biology, a lot of time you need to use a buffer. And the buffer basically, they can resist the change of the pH dramatically. Like this, if you don't have the buffer, okay, if you don't have buffer, then they change pH dramatically. If you add something, let's say you add acid here, but if you have a buffer, then they will resist the change of the pH, okay? And so from and here, so pKa, all right? So pKa, so remember, let me show you this again, pKa. Right, so pH equal to pKa plus log the conjugate base over the acid, all right? So let's say if you change the ratio of the base, okay, the base over the acid, all right? So let's say if you change it 10 times, if you change it 10 times, so that means the pH, right, would be equal to pK plus 1 or minus 1. And so that means if you change it 10 times here, let's say if it's a 10 over 1, even it's 10 times difference, the pH will only change 1, all right? Or 1 over 10 or 10 over 1, the pH will be just plus minus 1, okay? So that's why we have this, this pK, all right? So when the acid and base is equal molarity, then pH equal to pKa. If you change 10 times, then either pK minus 1 or pK plus 1. So that's what this means. If you have 100 times different, the pH only change 2. All right? So that's what this means. Can you see slide now?
Yes, now I see it.
Yeah.
Okay, good. So that's what this means, all right? It's based on the Henderson-Hasselbalch equation, so that you change the ratio, even the ratio is 10 times, 100 times different. The pH only change 1 or 2. That's it. Okay, so that's the reason why we need a buffer. Okay, so and then to choose the appropriate buffer, it depends on their pKa. All right, depend on the pK. If you need something at around pH 8, then look at this table. Then you will choose this buffer, trace edge, because the pK is 8.3. It's close to the range you want. That's how you choose the buffer. Okay, so that'll be for today. Any question?